Jinx.
Ah, no. Okay, so we get the window shared here. Where is it? Oh, I see. It's this one, I guess. Sorry, I should have had this prepared ahead of time. Hopefully you can see my browser window, the
Yep.
Rust programming language book. Okay, so we are this is the Rust programming language book club. We're going through the Rust programming language book, the Rust book, as it's called. And we're at chapter 5, using structs to structure related data. This is the first of 2 chapters on, I guess, user-defined types. Although I kind of looking through the rest of the thing, I think user-defined types are going to keep coming back and back, in that Rust is kind of a type-driven language. Where is that the right way to say it? I think you're encouraged to do type-driven development. Maybe I'll say it that way in Rust. So this is about structs. The next chapter will be about unions. Structs are, I think, sometimes called product types. This is combining several types together to make a type. Whereas I'm sorry, not unions, they call it enums. Enums are what's called sum types, and in Rust they're called enums for some reason, which just seems like a weird name, but in other languages they're called things like algebraic data types or sum types or unions, tagged unions. So again, as is always with this thing, we've all read this chapter kind of together, and please feel free to interrupt me with questions or observations or things I get wrong would be really useful. And yeah. So the main topics in this chapter are structs, of course, methods, which are special functions that you use on a struct, and there's also other associated functions you can use with structs as well. We'll talk about that. So first, let's talk about structs themselves. Here's how you define a struct. You start with the keyword struct, and then a name for your type, in this case, user, and then the brackets is where you put all the fields you want. So you name the fields, whatever you want them, a colon, and then whatever type. You have to say what type that field is. And that's how you build a struct. This is now your own type called user. They're very similar to tuples that we've discussed in a previous chapter, but the parts, you name them. Essentially, that's the main difference. They're similar to named lists in R, if you're familiar with R. So this is kind of the same kind of concept. You can get at the different parts of the struct in a similar way that you can with an R named list. Again, this defines a new type. So to instantiate a struct, you use this syntax. So here we're defining a new variable called user1. We're making it mutable. And then we put the type name user, and then we have to instantiate the different parts of the struct inside this bracket notation here, inside this block, essentially. And you name each field, and then you give it the value with a colon, not equals, which is something I keep tripping up on because that's how you do it in some other languages. But not equals is active colon, and then true, or variable colon, and then whatever the value should be. You can modify them like we did here. So I define user, then I'm going to say, oh, that's the other thing, right? So to get at the value of a field, use a dot notation. In R, that would be the $sign for comparison. Here's a dot, which is in almost every single other language. It's a dot, except for R that uses the $sign. So this is not something you will not run to again. And you can update it like this. Again, the only key thing is the entire struct has to be mutable to do this update here. So yeah, you instantiate it by creating specific values, and you can use the dot notation to get at it. And just to see that working, I'm using the Rust Playground here. Hopefully you can see this. If you're not familiar with the Rust Playground, I think the book talks about it. It's a great place if you just don't feel like standing up your Rust compiler, or for doing things like this where you're sharing code. It's very easy to do. And this is that same code again. Here's that struct that I defined. So you have to put in the same file or in a file that you include somehow. We haven't learned that yet with modules. But yeah, so we define the type, we instantiate one of the type variables, and then we update it, and then finally we can print it out. And again, we're accessing it using this dot notation, user.email. And you can run it and see what happens. There it is, user's email comes out. It whenever you use the Rust player or any Rust compiler when you're doing experiments like this, you always end up with all these little warnings about things you're not using. There's a way to probably turn them off. I said this is kind of a hint to that, but I guess I was recompiling. this is kind of a hint to that, but I don't actually know how to like do the not of this yet. So maybe somebody else knows how, but in the meantime, I'm just going to ignore the noise, as it were. So that proves it works, I guess, right? Let's see. It's convenient to define a constructor function to make instances, because sometimes you want to set values to be certain, when you're making a new user, they're always active. They've never signed in, or I guess signed in once if it's a brand new user. And the other parts we want to assign. So we're going to build a user, we return, whatever, to return a struct like this is just a last thing, just like usual. It's a last value. This is a value of type user, a literal value, I guess you might say. In any event, when we look at this, we see a lot of repetition. One thing is this user, and then user again, almost looks like a typo, but that is what you have to do. Fortunately, though, you don't have to do this. If you use the same variable name as the struct field name, you can delete that and just make a single username. Just one other point before I move on to that we will see that using constructors in this way is fine, but usually you want them to be an associated function. We'll see how to do that later. So this is that example of the shorthand. Now, instead of having username colon username, we just have username, and Rust knows what you mean. They'll translate that into username colon username. Yeah, that's basically that. This is called field init shorthand in the book, presumably in the Rust community as well. Another shorthand that is available that he talks about in this chapter is this struct update syntax. So this lets you take a struct you already have and then change some of the fields and creating a new struct from it. In this case, the notation here that uses this dot, and it's all one word. There's no space in there, dot, and then the name of the variable that you're stealing from, so to speak. And I say stealing because this does move data if the data is own variables. If the data owns variable, like email owns a string, and in this class, in this struct, you may remember there was another field called username, which is also a string. So user one is no longer going to be valid after we've moved it from into user two. I think I see a chat thingy.
That's not important.
Thank you. Yeah, allowed to go to, got it. Great. Appreciate that. So you so in that case, this user two is no longer valid because you had to move part of it because there was own data. It does turn out that if you give it a new username as well as an email, so that everything else left was stack data, it would be no problem at all. You can then still use user; it wouldn't move out. Just one of those things with weird things with the Rust, right? I guess the point is there's equals here. So if you see an equal, there's always a possibility of things moving. This is an assignment. It's just a funny kind of assignment. A struct update assignment, I guess you call it. They do mention a couple other special cases. There's something called tuple structs, which are just tuples, but you can give them a type name so that even though they're both tuples of 3 integers here, a color and a point are 2 different things and can't be used in place of each other. They're distinct types. And you can, however, access the elements of these tuples in the same way as we learned before with destructuring, or you can even use the 0.0.1. But if you're doing that, you probably want to go ahead and give these things names if you're doing that a lot. Then there's something called a unit struct, which is a struct that has nothing, no values to it. It's a singleton type. And I didn't really get clear to me on when you don't want to use that, but he did hint that it will be useful later as placeholders and markers when we deal with just traits, trait types, or type traits, I should say the other way around. Finally, we've been using own values so far. Well, what about structure? What about references in a structure? What's to prevent us from just having a reference to a username, a string slice in this case, right? And to the email. And it seems to look fine, right? It seems reasonable to me, but we can try that out on the Rust playground. And this is that same code again. So here's our 2 string slices, and we're saying, okay, let's define a variable. Here's our string slices, and we'll assign them, right? You try that, and it complains about something called a lifetime parameter. And this is one of those things in Rust that, much like async programming, I guess, is one of those things in Rust you have to learn to get used to. And I find it quite frustrating myself currently still. But it says we need to have a lifetime parameter. And the Stevens has a suggestion, we could try this, but we're going to learn more about lifetimes later. So we don't have to mess around with this anymore right now. Just the point is that so far we've been using owned variables, own data like string, and this makes sure the fields are always valid as long as the struct is valid. But if we put in references, we have to explicitly tell the compiler somehow how long those references are valid. And that's the topic of lifetimes, which is several chapters from now. Okay, so the next part of the book goes through an example program where you calculate the area of a rectangle. And this is kind of like a motivating example intended to be, right? So if we can try, we want to have a function that calculates the area of a rectangle, we'll call it function area, and we'll take in the width and the height, and we'll just multiply them together, and we'll get the area, right? So this is pretty straightforward, but, there's some issues with this, right? Well, what are the, this, we talked about this before, there's no named arguments. So when you call this, you might not remember which is first, the height or the width. Now, and the area doesn't matter, but for other functions, it might matter. We have no way to know what the ordering is here, right? And secondly, we want the area of rectangles, not the area of like two numbers. So we want to somehow combine those two numbers into something that we can call a rectangle. One idea is to use tuples. That'll bring the two numbers together at least, right? So in fact, there's a way we'll see later that we can even name this two tuple type as a rectangle if we wanted to, or we can use one of those struct tuples. What do they call that? What was that thing called? The struct tuple? No. I already forgot. I just talked about a second ago. Tuple struct?
Tuple struct.
Tuple struct. Okay, thank you.
Yeah.
Appreciate that. Rolls right off the tongue. But the problem with that is that now we don't even have argument names in here to know which is the width and which is the height. So we just got two numbers if we're looking at the source code for the function. Again, it doesn't matter for the area because multiplication is commutative, but nevertheless, this motivates the idea of using a struct for our rectangle. So now we have a rectangle struct. We've got two fields, width and height, both are integers here. And in our function, we can then define a rectangle. Now here we know this is the width and this is the height. And we call the area, we just pass in, now we're going to pass in a reference, of course, borrow it, and rather than move it. And now it's clear we're passing an entire rectangle. We don't have to worry about the order arguments or anything else. This seems to work really well, right? Much clearer our intent here. We want to calculate the area of a rectangle. It is a little bit more verbose than our original examples, but it's much clearer and less error prone, especially for bigger programs. And this is obviously a trivial program. You wouldn't write a program to calculate the area of a triangle. You just get your handy dandy phone calculator out, right? Triangle, rectangle, I would say. Okay, so good. But now that we have these user-defined types like rectangles, let's print what they look like. We want to be able to debug these things, right? And see what they are. And so we can try that. And well, I guess we can't print rectangles directly because why? Cannot be formatted. Oh, the trait standard format display is not implemented for rectangles. So this trait business, we're going to see a lot of as we go through the book. I think that's a later chapter. We're going to really learn about type traits. But for now, we do need to know a little bit about something if we want to print our triangles, because we have to implement this format display. Well, no, wait a minute. It says we can do this, right? So we can use this debug specifier instead of what we're using. So let's put that in. Okay, still doesn't work. And now it's because we don't have the trait debug. I don't know how to implement traits, either one of these traits, but here's the real helpful hint is we can put this specifier in on the rectangle, this derived statement, directive, I guess they call it, right? Isn't it called a directive? Derived directive? Well, anyway, we annotate it with this.
It's an attribute, no? Or is that different?
Attribute, that's it. Yeah, I think that's right. Yeah. And we add this derived debug attribute to the struct, and now it works. So we get out here that we can print out what our rectangle is. We can try the other one too, the pretty printed version, whatever see what that difference is. Makes it a little more spread out, I guess. So that's cool. So as long as we put this magic hashtag derived thing on top of our structures, we'll be able to look at them and see what their shape is. Until we learn how to do more about deriving traits later and implement display. The debug trait is obviously intended for debugging, and that's, you want to print later. You want to be able to print your structures in a more user-friendly way for your own data types, right? So I think I said all this. Yeah. I did all these things. Okay. Next is the debug macro, which is a helpful macro because you can put it in line inside of any expression and it will just go through the debug macro, so to speak. It'll take ownership of it, but it'll give it right back. And in the meantime, it'll print whatever it was, which is really cool. So you might have this complicated, really gnarly expression, like what is going on way deep down in there? And you can put that debug thing in there, which is kind of cool. Just again, I'll use the playground to show it in action again. Wait, did I get it? Is that it? No. Let me just close these other ones so I can. Here we go. Just to see what it does, because kind of another thing that's kind of cool. They don't is it gives the line number that was on in the column number of where, and also prints out what the expression was. So that's super useful when you're trying to figure out some complicated expression, and tells you what the value was at that point. Even for a rectangle, we can debug print it that way too. One other thing, just to point out, it puts this in standard error, not in standard output. Just something to be aware of. Yeah, it takes ownership, but don't be worried because it's going to go right back. it's going to return it at the end. Let's see. There's a lot more traits you can derive. Oh, there's an R version of debug somebody mentioned in chat. That's cool. Awesome. There's more traits you can derive. It refers us to Appendix C. There's things like you can automatically derive things having to do with like ordering, and probably the most important one is probably copy. You can derive copy, and as long as all the different parts of your structure also derive implement copy, you can automatically derive copy for your type as well. And yeah, we'll see more about traits in chapter 10. So that's the kind of the first part of this thing, just about the basics of structs. Anybody have anything to throw in here? Observations, concerns, complaints, questions? I think it's pretty straightforward. If you use programming languages like Python or C, this is pretty straightforward, I thought, other than the ownership issues, right? Not being able to, some funny is about putting references in your structs.
I guess one question, can you let like certain, I'm probably going to get the terminology wrong. Can you let certain fields of the struct be mutable and certain be immutable? No. It has to be at the level of the struct.
Yeah, that was called out. I haven't tested that myself, but it was called out specifically in the book. It said the entire struct has to be mutable, okay. Or yeah, that's different than like other languages, right?
I can imagine you could want like something where the ID remains immutable, right, but then other elements you update. So it's interesting. Okay, so methods are the next thing we're going to talk about. I'm just going to open this up so I have it available. A method is like a function. It is a function, but it's a function that's associated with the structure. And more importantly, it also takes in the structure itself as an argument, as a first argument. So the associated part comes from this syntax where it says implementing. I read this as implementing 4 rectangles. I don't know how you're supposed to read it, but that's how I read it. Implementing 4 rectangles, everything inside this block, right? This implementation block. So it starts here and ends here. Inside the implementation block, I can define as many things as I want to that are associated with rectangle. And for methods, they always start with this keyword variable. It's a variable and a keyword at the same time, self. So self, if you're used to Python, Python also does this. You take in self as a first argument. You can call other things. Everybody calls it self, but it's convention. This is not a convention. You have to use self. And other than that, so we define now the area as a method, takes in self and multiplies the self's width and self. Inside this code, self refers to the object being passed in. So the rectangle's width and the rectangle's height. Yeah, I said that. And to call the method, it's the same dot syntax used for accessing a field, except now it's a function call. This particular method doesn't take any other arguments, so it's an empty parentheses, but you still need the parentheses. The rectangle is passed in automatically. You don't have to pass it in here again. Automatically pass it out. And the book points out an interesting thing that if you're used to, like, if you use C or C++, or mainly C++ actually, you may be familiar with this arrow syntax that you use whenever you have a reference or a pointer to really a pointer to a object to call a method. Rust, you don't do that. You just use a period, even if you have a reference. So this syntax P1, P1 is a reference. Dot distance is the same as this syntax. Just automatically converts it, adds dereferencing or referencing as necessary to make it work, basically, which is kind of nice. If you've ever used C++, you know what I'm talking about. If not, that's just an aside. Let's just take a look at this in the playground. So here's our rectangle we've been playing with for a while now. Instead of defining a function for area, we've now defined it as a method inside this implementation block, taking self. And like I said, you just call it by, here we make a rectangle, then we call the method area, and then the self will automatically get passed in. There's nothing really special to see other than prints out a number at the end here, but 1,500 square pixels, there you go. So let's talk a little more about self because it kind of went quickly by that. First of all, you notice the syntax we used was ampersand self, which it wasn't proper, you know, isn't actually proper Rust syntax, except it is. Right? If it was some other variable, that would not be proper syntax. But for self, the special shorthands are used. So when you type ampersand self, it's shorthand for self ampersand self. In other words, you don't have to put in the type; it knows that. That's the trade-off for having a magic word for the self argument, is that you get a lot of nice shorthands like this. It wouldn't matter for language like Python where it's dynamically typed, or for statically typed language, it makes a difference. Okay, wait a minute, what's this though? What's capital SELF? We haven't talked about that either. Well, that's a shorthand as well. That's a shorthand for the actual type of the structure you're in. So in this case, rectangle. So ampersand self is actually shorthand for self ampersand rectangle. And the nice thing is you can use this self type other places in your method definitions, or as we'll see in associated functions as well. You can also use you can also do mute self for mutable borrowing. That's how you type that. That's the shorthand for that. And if you just wanted to, you could just use just self and take ownership. But they did say it's very rare to take in self as by moving it like that. Except when you're doing some kind of transformation type things on the object. So that brings us to associated functions. They're defined also inside an implementation block, just like a method is. The difference is the first argument isn't self, right? It's whatever you want. You can have whatever arguments you want. And the calling syntax is a little bit different. But even so, inside the block, you can use the self type to refer to the type inside the method definition. So this could be a type of associated constructor. So hey, this will build a square for you and return a square, right? A rectangle that is a square, I should say. Right. So they're defined in a implementation block, just like methods are. And this helps organize all the code related to your type into one place in these implementation blocks. That's kind of the cool thing there. I said that already. To call them, you use the type name and the scope operator like this. So rectangle : square 3 would make a square. A rectangle is a square. And we've actually seen this before many times because we've been using this string new and also the string from thing, whatever it's called. We've been using that already quite a bit, and these are associated functions. Let's see some other minor notes. One is that although we didn't do that in the book, he talks about this, that clearly you can have other arguments to your methods. You just have to list them after self. So this would be a function to determine whether or not one rectangle fits inside another. So you pass in the other rectangle when you called it. And the other thing to point out is that in this code, I actually wrote this as two separate implementation blocks just to show that you can. You can have multiple implementation blocks in your code for the same type. They don't have to all be in the same place. And then this is not really neat here, but it does mention that this is something that'll be very useful when you're defining generics and traits in chapter 10. Yes, a type can have multiple methods and answering a question in chat, multiple methods and multiple associated functions with them. And generally have a lot. Let's see, I think we're at the summary. Yeah. So basically in summary, right, we have structs that let us define our own custom types that combine smaller types together, build up like Legos or bigger types. We have methods and associated functions to help define behavior for your types inside implementation blocks. And next chapter, we're going to go on to another type of custom type called enums. A couple of contrasts though, is you'll notice that these structs are, if you're used to things like Java, C++, Python, languages like that, you'll notice that these structs are not like Python classes in one way, in one important way, and that's you don't never say what their super type is, because Rust doesn't have that concept, at least not in terms of structs. There's no implementation inheritance, or there's a minor type involving traits, but generally there's not much support for implementation inheritance in Rust, and I consider that a good thing because implementation inheritance, I think, causes more problems than it's worth. I think that's it. Yeah. I think I did that almost. I was debated thinking about whether or not this could be combined with the chapter on enums, but I wasn't sure because I wasn't sure how much interruptions there'd be questions, but there wasn't very much. So you guys are all